Good evening, everybody. This is Obi-Wan Pez for In Simplex Vachenko. We are doing Cracking the GRE Math Subject Test from the Princeton Review, 2nd edition, 2002. This is the one that I used and my spouse used back when we were doing our GRE before going to the Johns Hopkins University. So, currently, we're just passing the halfway point for, the Calculus 2 material. So if anybody has any other questions and stuff like that, feel free and stop me, because I'm not going to stop, pretty much, unless somebody asks for something else. So feel free to ask for any other material that you'd like to ask questions about, be it math, be it education, be it just, getting used to college life, that sort of stuff. We will do just about anything that you would want to talk about. So, let me just make sure here. I think we want to shrink this down just a bit. See, it's getting it is very large. My window was, in fact, I believe, too large for, okay, there we go. A bit too large for the space that it was taking up here. Anyway. Number 24. The function f of x is equal to the integral from e to the x to e to the 2x of t natural log of t dt has an absolute minimum at x equals 0 and a local maximum at x equals blank. So for this, we're going to do our usual, come through, natural log 4, negative natural log 4, negative natural log 2, natural log 2, 1, or natural log 4. In other words, natural log 0, nope, nope, natural log e, there we go. So yes, there is a reason why it was in this order. All right, sorted by the overall value, which is going to be in effect the same as the sorting by the argument also. Right. So for this, there are a few ways of doing it. One is that we could also try to find f prime of x and then be able to do try to find what minima and maxima we have. So, the proper mathematical way of doing this is going to be that we want to set this up as the derivative dx of, and then here we want our function that we have. So just for starters, e to the x to e to the 2x, take the integral of t natural log t dt, And then we know from the Fundamental Theorem of Calculus, this is not going to go well for us with all of this stuff here. So instead, what we have to do is break it up as two pieces. ddx of. Here we take the integral as we go from 0 to, nope, not 2, e to the 2x t natural log t dt, and then subtract the integral as we go from 0 to e to the x of the same. So when we take the derivative with respect to x of integrals that go from a constant up to a function value, whatever function value it is, in terms of x. So specifically in terms of the deriving variable, then we're going to end up, in effect, just replacing the bits that we have. Now this does mean that we are going to have to work with something that isn't just x, because normally Fundamental Theorem of Calculus says that we have ddx of the integral from any constant really up to just x. And then we do some function, I should not use f, some function of t dt, and that's going to end up being the same as just g of x. Now the thing with this is that we're taking this particular integral. We can describe this slightly differently, as we're taking the derivative as a to upper limit of x. Hey. Hey, Zach. Did you read? Nice. So happy to see you were working with differential equations. Hi, everybody who doesn't know me. My name is Obi-Wan Pez. This is N Simplex Pachinko. I'm also on that raid. Hey. Actually, come to think of it, right? I wasn't. Oh, that's sad. I wasn't on my moderator account, so thanks for dragging me over. So we're going to be working on, for anybody who doesn't know, cracking the GRE math subject test. We're working on the Calc 2 stuff at the moment. Coming up through the middle of the review, or the final exam for the Calc 2 stuff. So after that, we're going to be moving on to Calc 3, and then differential equations and linear algebra. I don't remember exactly what order it's in. We'll get there. So here we were talking about the Fundamental Theorem of Calculus and what happens when you have specifically something that is not following the Fundamental Theorem of Calculus exactly. So when we have different limits like this, oh wait, hang on. There's a laser pointer somewhere. Oh. Is it here? No. Pointer? Oh. I lost it. That's alright. Yeah, the category is supposed to be just math. That's, That was an oversight. Thank you. How you doing, Max? So anyway, yeah, the basic idea here is that when we have a an integral that has limits that are not following the fundamental theorem of calculus. One, the fundamental theorem of calculus said we have to have a constant in the lower limit, and then in the upper limit we're using the same variable as what we have for the derivative out front. And when we do that, if we just take the derivative with respect to x of the integral from a to x of g of t dt, that's just the same as g of x. And we've worked out this in the longer form before. And I'm going to show what happens in using a function, u of x, as the upper limit of the integral for in the long form. So what we're going to do here is we see that when we take the integral of a from a to upper limit u of x of the function g of t dt, what we get is the derivative d dx of the function capital G of x, just representing an integral of the function lowercase g. That's it. Sorry, g of t. Let's do this again in long form so that we understand the concept first. The limits for this are from a to u of x. So if anybody hasn't seen this before, or if you've seen it but like maybe it's been a while, this might be a good refresher. So this is going to be d dx of, let's move that again, d dx of, here we have g of u of x minus g of a. All right, then we take the derivative d dx. And what happens here is that the derivative of g, big G, is little g of u of x. But then we have to use the chain rule, so we multiply this by then the derivative of the inside, which is u prime of x dx, which, again, since we have dx as part of our differential operator that we're using outside, it's just going to divide out, no problem. Zach's going to be upset with me saying that, but nonetheless. And then we take the derivative of g at a, which is a constant. So we just get a minus 0. So this says that d dx of the integral from a to u of x of g of t dt is going to be equal to g of u of x times u prime at x. That's how I know you're still paying attention. So anyway, that's what we're going to get. So using that concept, we're going to use that over here. The first step was to separate our integral such that the lower limit was always a constant. So we can do it to 0. It doesn't really matter. You can do it literally to anywhere. It doesn't make any difference. To 0 just makes the most sense. I lied. Technically, we can't do it to 0 because natural log of t will be upset with us. So, fine, we'll do it from 1 to those function values. All right, it's a technicality, but it still needs to be discussed, right? And when we subtract these limits from each other, when we subtract the functions from each other in the appropriate ways, it ends up working out the exact same way anyway. So, okay. All right. So now we take d dx, the derivative with respect to x of these particular functions, and then what's going to happen is the first one is, again, going to follow the same rules that we did over in the other stuff. So this is going to be just g of our upper limit. So now our t becomes e to the 2x. Our natural log of t becomes the natural log of e to the 2x. And then our dt effectively becomes du dt. Right, so here what we end up with is multiply by the derivative of the upper, derivative of the upper function, which is e to the 2x times the derivative of the inside, which is 2. Okay, and then we subtract, parentheses, the exact same thing for just e to the x now. So we're going to have e to the x times the natural log of e to the x times the derivative of the upper function, which is e to the x. Which then is going to get us the two e's are going to multiply together, so we get e to the 2x times e to the 2x is e to the 4x times natural log of e to the 2x is going to be 2x times the 2 from the end. Okay, minus e to the x times e to the x is e to the 2x times natural log of e to the x is just x. So this is 4x e to the 4x minus e to the 2x times x. I guess we'll do that the other way around because it makes more sense. X times e to the x. Okay, now this is the derivative, and now we want this to be equal to 0 in order to find the maximum. So then this part, this like sub equation, is then going to be set equal to 0. We can pull out only a single e to the x and an x. And then left over is going to be 4 e to the 3x minus 1 is equal to 0. And now we could do the zero product property, just like we did in, Algebra 1. If we have two things that are multiplied together, and their product is equal to 0, then either of those things has to be 0. So either we've got x e to the x is 0, or 4 e to the 3x minus 1 is equal to 0. We already know this one. This is x equals 0, which is the absolute minimum. Yeah. Absolute minimum, which was given at the beginning of the problem. Hey, famished? Yeah, no, I messed up. Blueprints was last night. Over here, we've got 4 e to the 3x is equal to 1. E to the 3x is equal to 1/4. I feel like this is incorrect. Must have screwed up somewhere. Take the natural log of both sides. So we're going to get 3x is equal to the natural log of 1/4. And therefore x equals 1/3 natural log 1/4, which is not one of our possible solutions. So, yep, I messed up somewhere. So, error resolution is an important part of mathematics. Now we need to figure out what went wrong and where. If anybody sees it, feel free to shout out. Thank you, Max, for the follow. Okay, so at this point, we need to figure out right, e to the 2x, take its derivative, it's going to be e to the 2x times 2. So we've got that here. Over here, we got e to the x, so its derivative is just e to the x. And then t, natural log t, is something that we're going to get in both terms. In this case, t is being replaced by the upper function in each integral. So e to the 2x and e to the x. Yep, sure is. That drops the 2x, becomes 4x. That combines to become e to the 4x. That combines to become e to the 2x, and that drops the x. Yep. Oop. Ah. There we go. There's supposed to be a 2 there. A. So that means that 2 of our x's get dragged out. I feel like that doesn't help much, but nonetheless. Okay. Ah, nope. That does work for us, actually. Ever so slightly, but nonetheless. Makes all the difference. Okay, so here's the thing, right? It didn't actually change all that much. And this is also one of the reasons that like teachers want you to write your work out a lot. At least until you become practiced with a particular thing. It's that in cases like this, I made such a minor error. I didn't have to erase everything and start over. I just had to erase one number all the way through my little calculations here. And then I didn't have to do any real mental work in order to figure out like how to fix that. So here, this is going to be x equals the natural log of 1/4 raised to the 1/2, which is the square root, which means that this is the natural log of 1/2. Right, the square root of 1/4 is a half, which is equivalent to, because we have a half on the inside of this, we could say, well, this is 2 to the negative first. So this is negative natural log 2. All right, that is a solution which was up above. Negative natural log 2. Bingo. Right there. This is not one of the ones my spouse did. Either she was very confident or just annoyed. All right, if anybody has any questions on this stuff, please let me know. If you have questions on other things, including mathematics up through, generally speaking, differential equations and other, like, I've taught stuff through sophomore level. So differential equations, multivariate calculus, linear algebra, and I've done higher level differential equations, machine learning, a few other things. So I can maybe, in theory, help out with some of the other stuff. So it kind of depends on what you got. Integral from -1 to 0 of x squared times x plus 1 cubed dx is equal to what? Right, so evaluate really just means don't do that. Right, so a few different ways you could do this. I'm slightly annoyed with it. It's fine. We could multiply everything out. That's a disgusting way to do it. Don't do that, if you can help it. The issue with setting this up for u is that a du would just be 1. So we already have dx. We don't need it. Right, let's... Okay. So the absolute terrible way to do this would be we know what x plus 1 cubed is because our name is n simplex pachinko. And so, of course, we know how to distribute binomials. And in fact, any polynomial to a power is super easy because that's the entire channel name. And in this case, we would get x to the 5th plus 3, x to the 4th plus 3, x cubed plus x squared. But again, that's gross. It's perfectly viable. I just don't like it. So if we flip it around, u is equal to x plus 1, then x is equal to u minus 1. We could do slightly less work, and I do mean slightly. These are where x is equal to -1 to 0 as our limits. And then this would give us our u going from 0 to 1. Since u is just x plus 1, we add 1 to each of the limits. We're just going from 0 to 1 instead. This would be u minus 1 parentheses squared times, u cubed. And dx is the same as du. But that doesn't mean you can actually put mixed variables in there. Don't do that. Right, so du equals just dx. X, God, I am really going all out today. Okay, again, this is slightly less work from this standpoint. So, again, if we were to expand this out, this is u squared minus 2u plus 1. And then we're multiplying by u cubed. So this is going to be u to the 5th minus 2u to the 4th and plus u cubed. So if we're doing this, u goes from 0 to 1 du. Then this one is going to be equal to 1/6 u to the 6th minus 2/5 u to the 5th plus 1/4 u to the 4th, evaluated from 0 to 1. In this case, we're just taking the sum of all of the coefficients. So 1/6, 2/5, negative 2/5, and 1/4, and then just summing them up. And then we get a minus 0 because 0 plugged into all these just makes that go away. So, easy enough. Lowest common denominator here is going to be 60. Yes. So we get 10 minus 24, and then plus 15, which is going to be equal to 25 minus 24 is 1/60th. Hey, look at that, it's an answer. D. So, slightly less work, but you have to remember the trade-off that you can do there. If anybody has a different way to do this, please let me know. I know that there probably are. I don't think there's any good other substitution way to do it. I think this is it. But, yeah. Okay, so if we had done it the other way, this would have been going from -1 to 0 as x dx. This would have been 1/6 x to the 6th plus 5 would have been 3/5 x to the 5th plus 3/4 x to the 4th plus 1/3 x to the 3rd, evaluated from -1 to 0. 0 would have cleared it out, and then we get minus all this stuff. So all of the evens would become negative, and all of the odds would actually become positive because we would also be subtracting all the terms with a negative power. Sorry, with a negative number going into an odd power. So this is going to be 3/5 plus 1/3 minus 1/6 minus 3/4. And again, we got a 3, a 5, a 6, and a 4, so 60 is going to be our, oops, too big. 60 is going to be our common denominator. 5 is going to be 12 of those is 36 plus 20 minus 10, 3, minus 15 times 3 is 45. So here we get 56, and minus 55 is also, again, 1/60th. So we do get the same thing. Nice. All right. Anybody have any questions on this sort of stuff? Thanks, Max. Yeah, we're getting to 10:30 my time, so as long as the coffee keeps up, it might be okay. But have a good night. I'll be here, so you know where to find me. And Mondays and Wednesdays are my usual mathy type stuff. Mondays are usually math communication, and then Wednesday are calculation. And then we do gamey stuff the rest of the week. So see you later. Have fun. Righto, 26. Okay. If bracket x denotes the greatest integer less than or equal to x, so we would also know this as the floor function. These being alternate notations for it. Then the integral from 0 to 7/2 of greatest integer function of x dx is going to be equal to what? Right, so knowing our way around the function is going to be probably the better point here. So here for greatest integer, we say that it's less than or equal to, yes. So we start with closed at 0 going to open at 1, up to closed at 1, 1, going to open at 2, 1, closed at 2, 2, open at 3, 2, closed at 3, 3, open at 4, 3. Then we're looking at taking the integral. So we're going to go from 0 to 1. We get a value of 0 in here. So that's easy enough. Then when we go up here, this is integrable, despite the fact that there is each of these discontinuities, because they're only at a single location, and the exclusion of a single number in terms of integrals is not going to have any effect. So we can have something have an integral over an open area, as long as there's like a finite number of discrete discontinuities. something like that. Okay, this is a 1 by 1 square, so that's going to be 1. Going up to 2, coming across, this is a 2 by 1 rectangle. So that's going to have an area of 2. Okay, and then going up to 7 halves is 3.5. So we're going to go up like this, come across there, and down like that. This is now going to be a 3 by a half. So that is going to have an area of 3 halves. Right, so now 1 plus 2 plus 3 halves is going to be 3 and 1.5, or 4.5. The answers for this were possible answers for this were 5 halves, 7 halves, 9 halves, 17 halves, 37 halves, which, oh gee, lucky for us. Right, we do have our answer. 4.5, or 9 over 2 is going to be right there. Another way to realize this might have been that if you recognize that the area was going to be the sum as I goes from 0 to let's see. The limit was going to be 7 halves, right? So that means right, this is the integral from 0 to b of the greatest integer function x dx. Okay, of just I. Yep. Plus the partial bit. So this would have been the difference between greatest integer b and b. B would have been bigger. B minus greatest integer b multiplied by the height would have been greatest integer b. So this might be a way to just kind of think about it. Not that you'd actually want to like pull this out during an exam. Like, why on earth would you do that? But looking at it, you could think to yourself like, okay, I need what's essentially going to be the sum of all integers going up to a particular point. When is that going to be? Well, it's up until the greatest integer, which was 3. Ooh. -1? Yeah, -1. Right. And then this one represents the height that we're getting off of it, which completes the total going from 0 to greatest integer b. But we only have, instead of a 1 in this case, a width. For the summation, the width is always just going to be 1. For the partial part over here, then we say, what's the width of the extra bit? That's going to be b minus greatest integer of b. If b and the greatest integer of b are the same number, then it's 0. Right? We're not counting anything. And then greatest integer b over here, as well as greatest integer b minus 1 over here, are the heights of all the bits that we're getting to. Yeah, right, because if we're doing 1, anything from 0 to 1, if we count 1 as our upper limit, then it's going to be 1 minus 1 ends up being 0, and so we're just counting I as 0. That's it. If we're going out to 2, that's going to be 2 minus 1, makes it 0 to 1. So we're going to count the integers 0 and 1. Okay. I like it better now. This takes account of everything, but again, nobody would actually like expect you to be like, oh, well, let's make sure you know how to do the formula for this thing, because that'd be crazy. 27. If f of x is equal to -2 times x plus 1, where x is less than or equal to 0, and k times 1 minus x squared, where x is greater than 0, then find the value of k such that integral from -1 to 1 of f of x dx is equal to 1. Okay. So here, this is going to be the integral from -1 to 0 of f of x dx plus the integral from 0 to 1 of f of x dx. We can take this separately because we know how to work with integrals. We can separate them out and say each of these individual integrals are easy enough to do. We'll work with them separately. So here, this is the integral from -1 to 0 of -2 times the quantity x plus 1 dx plus integral from 0 to 1 of k times 1 minus x squared dx. Right? And then this whole thing here should be equal to 1. Right. So this first one here, we go -2 times the quantity, and then we're just doing the integral of x plus 1 dx. And the integral of x plus 1 dx is going to be 1/2 x squared plus x, evaluated from -1 to 0, plus k is a constant, so that's going to come out. And then we're left with 1 minus x squared dx. When we take that integral, that's going to be x minus 1/3 x cubed, evaluated from 0 to 1 is equal to 1. So this is going to be -2 times the quantity. 0 is going to clean this out, so we have nothing there. And then -1 is going to be subtracted, so better if we do it this way. 0 minus parentheses, plug in a -1. So this is 1/2 -1 squared plus parentheses -1 plus k times quantity. Here, 1 is going to be 1 minus 1/3 1 cubed, minus 0 is going to clean this one out. And that whole thing is going to be equal to 0. No. That whole thing is going to be equal to 1. Jeez. All right. This -2 is going to multiply a -1/2 from this bit, and that's going to become a +1 times -1 squared is 1. -1 times -1 is +1 times -2 is going to be -2. Plus k, now we'll leave it there, times the quantity. 1 minus 1 cubed is going to be just 1. So times 1/3 is going to be 1 minus 1/3. So 2/3 equals 1. So 1 minus 2 is going to be -1 plus k times 2/3 is going to be equal to 1. Add 1 to both sides becomes 2. 2/3 k equals 2. Multiply by 3/2. So we get a 3. K is equal to 3. That is an option. Oh, good. -1, 0, 1, 2, 3. 3 was our selection. All right, 28. Integrate. Take the integral of x squared dx. Nope. Well, that's fine. Divided by square root 1 minus x squared. So, could do integration by parts. It's kind of gross, but it could work. So if u is equal to x squared and dv is equal to 1 over Square root, no, that's probably not going to work. Hang on. Let u just be x. Well, actually, either way could work in theory. So we can make this x over 1 minus x squared. That might actually give me the wrong thing that I'm thinking of, but... Okay, so this would be some constant times square root of 1 minus x squared in the numerator. And then du would just be dx. And for anybody who does not know out there, we got some really awesome other math friends who do some other really awesome math streams. So go check them out. Academy of Useless Ideas, Slim is over there. We got Dr. Gold at Actual Education, Don Factorial, E.N. Stuckey, Zach, you should know because he came here from there, probably, at e to the 2i pi, Merriweather Remark, Penn Center, Phobos Dream, Physics and Depression, Talos Teaches, The Tutor Wizard, and we also have some... Oh, and Matt. And Math Pond as well. Keep meaning to add. Sorry. And then we've got some other study buddies who like to stream while studying a particular thing, and many times it is also math. So you can go check them out. Rendeo, Math Spellbook, Fizzbuzz, Suna Ao, Walking Stick Library, and Damie at Damie VTuber. So if you go check them out, they got some awesome stuff. And we also have a YouTube, well, 2 YouTube channels, one for gaming and one for math, at Obi-Wan Pez and at nsimplexpachinko6542. If you just type in nsimplexpachinko into the search bar, you'll also get this math. So we'll be there. We're going to start ads here in just a minute, so we'll be back shortly. Let's see. We need a 2. In order to integrate that properly, we also need a 1/2. So actually that one can go away. For the exponent of the radical to come down. So 1/2 times 2 gets us just 1. We don't have to do anything. That's nice. So we just end up with that. Yeah. Okay, so uv minus integral v du. Creates a slightly different problem. Anyway, we'll be back in 3 minutes. See you all back here just a little bit. Thanks so much for coming. Alright, maybe a little hard to prove or something, but down here, I promise. Let's not knock over the painting. And a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Good enough for today. Okay. We'll keep the plus c added at the end. Just a reminder, right? Any of our constants, it's not going to matter. Eventually it will accrue. And all of the constants will add together to create another constant. So we won't worry too much about it. Minus. Okay, so at this point, what we want to do here is we can let x be equal to cosine theta. Let's do sine just because derivative won't be negative. It's not going to matter. Dx is equal to cosine theta d theta. And so this is going to be the integral of the square root of 1 minus sine squared theta times cosine theta d theta. X root 1 minus x squared minus, here we've got the square root of cosine squared theta times cosine theta d theta. Okay, which is then going to become cosine theta times cosine theta d theta, which is the integral of cosine squared theta d theta, which is the integral of, and here our cosine squared, we can use the power reduction formula, which, if you don't remember it, that's perfectly fine, because you should be able to remember what the double angle theorem is. So cosine of 2 theta is going to be cosine squared theta minus sine squared theta, or 1 minus 2 sine squared theta, or 2 cosine squared theta minus 1. And then when you start changing stuff around, this is where we get cosine squared theta is going to be equal to right, cosine of 2 theta plus 1 all divided by 2. So 1/2 parentheses cosine of 2 theta plus 1 d theta. Okay, so from here, we get a 1/2. We need a 2 outside of our cosine of 2 theta in order to satisfy the chain rule, which then means that this is also over 2. Which is going to get us the sine of 2 theta. Plus, this is a 1/2 theta. Plus c. All right, then when combined with all the stuff from above, is going to be x times the square root of 1 minus x squared minus 1/4 sine of 2 theta. Ah, right. Yes, theta. That was why I color-coded it in the first place, was to remind myself not to skip on changing it back. So this is going to be a minus 1/4 sine of 2 theta is going to be 2 sine theta cosine theta. So this is times 2. Sine theta is just x. Cosine theta is the square root of 1 minus x squared. Okay, and then plus 1/2 theta is going to be the inverse sine of x, or arcsine x, and then plus c. Thank you, famished. You know how it usually works. It's fine. All right. So what do we get for possible answers? A is 1/2 parentheses arcsine of x minus square root 1 minus x squared plus c. Oh dear. B is going to be 1/2 times arcsine of x minus x times root 1 minus x squared plus c. C is 1/2 times the quantity x times arcsine x minus square root 1 minus x squared plus c. D is 1/2 times arcsine of x minus, B was plus. D is minus x root 1 minus x squared plus c. How about the other one? No. Those are all minus as well. Okay. And then E is 1/2 arcsine x arcsine x. Oy. X arcsine x minus the square root of 1 minus x squared plus c. So let's see. We're not quite there, but we're pretty close. Okay, so here, this is going to be a minus 1/2 x square root 1 minus x squared. This is going to be a plus 1 x times square root 1 minus x squared. One half arcsine x, and then all plus c. So here, this is going to be a 1/2 parentheses x root 1 minus x squared. Okay, plus the 1/2 gets pulled out, so it's just arcsine. Or to put it in terms of what they actually have up there, right? 1/2 arcsine x plus x root 1 minus x squared plus c. Okay, that was a thing. Which one was it? B. Yep. Righto. If anybody does have any questions, let me know. 29. What is the area of the region in the first quadrant bounded by the curve y equals x arctangent of x and x equals 1. Penn, Damie, me, Zach was just on. Megamorph, good to see you again. Angels will show you a sine, but archangels will show you an arcsine. Well, the arcsine gives you an angle. So the archangel gives you an angel? We're stretching that metaphor pretty far. Okay. All right. Arctangent normally looks like this. However, because it is x times arctangent, this is going to be multiplied by a larger and larger and larger value every time, which may very well end up being like pseudo-linear. Oh, this also goes off to the positive region, but that doesn't matter. So the arctangent gets you a negative value in the negative region, but the x also gives you a negative value in the negative region. And then if this is 1, we want to know what the area of this is going to be. This is probably a terrible representation, so why don't we just actually look at it. Yeah, okay. Doesn't look that bad. It is going to be approximately linear as we get further and further out. Right, because the arctangent, oh, literally, yeah, the arctangent is asymptotic to a constant. So it's effectively going to become, what is that, pi over 2. So it's going to be effectively pi over 2 times x. So that needs to be curved the other way. Yep. Make it more Demi VTuber. So not quite Demi. As awesome as it would be to see Demi Moore. Oh, that's true. Yeah. Because it will eventually just incorporate it. And yeah, rather than effectively, you can just make it asymptotic. Woo. So actually, that means it's going to come from under it, right? Yeah. I mean, yes, but since I'm not just doing this as what's the best way to solve the exam, I am trying to build up some intuition for students or whatever. I don't know, something. Anyway, I would be suspicious if you weren't. Okay, so anyway, this thing, right? So we want, what is the integral from 0 to 1 of x arctan x dx? So, I mean, ugh. If we do this as we did the last one, and say that it's going to be integration by parts, then we probably want to like you said. if we want to do this, we could say that u could be arctan, and so therefore du is going to be 1 over, or dx over, 1 plus x squared. And then dv is going to be x, dx. And so v is going to be 1/2 x squared. Yeah. No, that'll work. Yeah, that'll work. Okay, this is going to be just a two-step process here. So from 0 to 1 of, no, hang on. If we're doing integration by parts. All right, then this is going to be equal to uv, so 1/2 x squared arctangent of x minus integral, also from 0 to 1, and this is evaluated from 0 to 1, of v du, so 1/2 x squared times dx over 1 plus x squared. This is fine. Right, this will be 1/2 1 arctan of 1 is a nice number, minus 0 for all the rest of it. And then minus here the integral, 1/2 integral from 0 to 1 of x squared over 1 plus x squared dx. Then we could say, you know what, let's do a simple substitution in this case where 1 plus x squared is going to just be u. And so therefore x squared is going to be u minus 1. Fine. No, that works. That works, because then dx is just going to be du as well. Right? They're of the same order. This is fine. You could probably figure it out some other way, but whatever. This is good. Okay, so this is going to be 1/2 add 1, subtract 1 on top. Yeah, that could work too. That's probably the nicer way to go, honestly. Right, arctangent of 1 is going to be pi over 4, minus 0, so that's just gone, minus 1/2, right, times, take the integral from 0 to 1 of, this is going to be just 1, so that's nice, minus 1 over 1 plus x squared dx. Right, so this is going to be pi over 8 minus 1/2 times the quantity. Here we just get x from 0 to 1, minus, and now here that's also an arctangent because we literally just had that. Also from 0 to 1. Okay, pi over 8 minus, here it's just 1, so that's a half, and then plus a 1/2. Arctangent from 0 to 1 was getting us, again, pi over 4. Oh. Well, okay, it doesn't get rid of itself, so that's easy enough. Yeah. Pi over 4 minus a half. Ah, gross. All right. They always give them weird formulations of the answer, which are, correct, but they don't quite look like you expect them to look. Pi over 4 all over 4. Or pi minus 4 over 4. Pi minus 2 over 4. Pi over 4. Pi plus 2 all over 4. Or pi plus 4 all over 4. So the one we have is pi minus 2 all over 4. We're going to multiply both top and bottom by 2. Here and here. So B. Righto. 30. Simplify. E raised to the integral from 3 to 5. They actually wrote it out in here, exp integral, but, same thing. Dx all over x squared minus 3x plus 2. Nope. Already did the dx, so we don't need that. Equals question mark. We don't do that. Okay. A, B, C, D, and E. I will endeavor not to read the reminder on it, but we'll see how it goes. 3/8, 2/3, 4/3, 3/2, 5/3. Okay. With a simplification of this, we're going to want to break this up via partial fractions. So we need to know what x squared minus 3x plus 2 is. Easy enough there. Have to have the same sign based on the plus 2, and the larger sign is negative. So this is going to be 1 over parentheses x minus 2x minus 1, which we then want as partial fractions is going to be a product of a over x minus 2 plus b over x minus 1. We then multiply through by x minus 2, x minus 1, and we get 1 is equal to a times the other one, so x minus 1, plus b times the other one is x minus 2. What's the sum and what's the product now? Did I misspeak? Okay. Yeah, the product of x minus 2 and x minus 1 is then going to be, sorry, the fraction with a product in the denominator is then going to turn into the sum of a over x minus 2 and b over x minus 1. Honestly, does not surprise me in the least. Students would catch me out on that stuff all the time. I'm like, what? Oh yeah, okay. I'm sure there were so many more that they missed just because, you know, I wrote it correctly. Okay. So there's a few different ways you could do this. One is if we just let x, not a, x equal 1 for a second, then we find that we get 1 is equal to, the a term becomes 0, and then the b term has a negative 1 attached to it, which then means that b is going to be negative 1. And if we let x equal 2, then we're going to get 1 equals, the a term is going to have a 1 attached to it, and the b term is going to go to 0. So here we end up with b equals negative 1, a equals positive 1, and then we could just work our way through that. So this is going to be e raised to the integral going from 3 to 5 of, what's it again? A is 1, so 1 over x minus 2, right, minus 1 over x minus 1, because b is negative 1, dx. Logic set of theorem tells us that we know there are some a and b, which makes this a true identity. Yep. Right, yes. So this has to be true for all values of x, and therefore we can select very convenient values for x, which eliminate the other stuff. Alternatively, right, we can go the other way and say, now, I must be mathematically pure in the way that we do this. We say that 1 is going to be equal to ax minus a plus bx minus 2b, and then rearrange stuff. So we get 1 is equal to a plus b multiplied by x plus a negative a minus 2b. And we also know that the other side has a plus 0x. And because this has to work for all possible values of x, the only way that that's going to be possible is if the coefficients are the same on either side. And so here we get a 0 is equal to a plus b, and 1 is equal to negative a minus 2b. Right, yeah. Although if there isn't an a and a b that actually work, I believe this version ends up collapsing into nonsense. Okay, so if we got a plus b is equal to 0 and negative a minus 2b is equal to 1, then we could do this as a system of equations, add straight down, we get 0 minus b is equal to 1, so therefore again b is equal to negative 1. Back substitute through here, and a minus 1 is equal to 0, which implies that a is equal to positive 1. we're verifying that, yeah, it ends up being the same thing. You could do it either way. I tend not to like this version of it unless the equations are super simple, just because I don't want to make mistakes. But it'll still work. Like, mathematically, it should still work no matter what. But there might be weird sub cases that don't work for some reason. So just be aware, be careful. All right, this is going to be e to the. Here, the integral of 1 over x minus 2 is going to be the natural log of the absolute value of x minus 2. Evaluated from 3 to 5. And then we get a minus natural log absolute value x minus 1, also evaluated from 3 to 5. Which is going to be raised to the natural log of 5 minus 2 is going to be 3, minus natural log of absolute value of 3 minus 2 is 1, so that's a nice 0 there, minus natural log of 5 minus 1 is 4, minus a negative natural log of the absolute value of 3 minus 1 is 2. So when we get this, we have to combine everything first. Alternatively, we could also separate these out as separate e's, whatever you feel like. This isn't going to matter. So, right, so we could do this as e to the natural log of, parentheses, 3 times 2, the things that we're adding together, get multiplied as arguments. Right? These are the exponentials that we are multiplying together. The natural logs themselves are exponents, so they represent exponents. So when we add exponents, we multiply their arguments, we multiply their exponentials. And when we subtract an exponent, we end up dividing its exponential, like the exponential term. So this is then going to be over 4. This is going to have e to the natural log. That goes away. They're inverse operations of each other. So now we just get 6 over 4, which is 3 over 2. Oh, repeated roots. Yeah. So you do, like, if you set it up correctly, then I don't think you're going to have much of a problem. But, or if it's only repeated roots, I guess you might have an issue. Yeah. Right. But then you're still doing the same thing. You're just going to end up, yeah, right. Okay. You're just going to end up plugging in a different value twice and then using that as the system of equations, which works fine. Takes as much work. Well, okay. Maybe not quite as much work as this then, if it has a longer polynomial to work with, but it'll be all right. Okay, so 3/2. Found it. It's D. I'd like to finish this page, which goes through 32. So I got 2 more in me. That's not a problem. Calculate the area of the region in the first quadrant bounded by the graphs of y equals 8x, y equals x cubed, and y equals 8. Okay. y equals x cubed. Going to look, roughly speaking, like this. We know that at 2, we're going to hit y equals 8. And y equals 8x. Right, that's going to get at 1. It's going to hit there. Let's do a line tool. Woo! Probably could have done it for the other one, but it's all right. So we want, what is the area of this thing? Two major ways to do it. There is the ridiculous way, which is we want the area of the region all right. That's not going to work very nicely. We have the area of the region, and here we have to split it up. This is going to go from 0 to 1 of y equals 8x minus woohoo! Hey Penn Center, how's it going? And hey everybody who's coming on over. My name's Obi-Wan Pez. This is N Simplex Pachinko, our mathematics channel that we do. Well, I do also gaming type stuff on here, but over on YouTube we use at Obi-Wan Pez for gaming and at NSimplex Pachinko X6542 as our mathy type stuff. Don't want to divide your attention, but I hope this raid is a plus. Absolutely. Probably Orion. Welcome on in. Oh, man. We just played Orion. Yeah, we're doing some Calc 2 final exam type stuff. We're going for another couple of problems. The final exam that's in cracking the GRE is 50 questions long. So we've been spending like, I don't even know, probably 6 weeks on this thing alone just because I've been so distracted with moving and like I get into stream and I'm just like drained. I'm just like, so we get 2 problems done and then I'm out. So we've done like 6 tonight. It's pretty good. These problems are also a little bit quicker, so. So no, we're already in a new place. Our old house, which was just over the hill from where we are, the owners wanted to move back in. So they were like, yeah, we know you've got 15 months left on your like overseas stuff, but you know, we want to move back in. And we're like, okay. Which also means that we need to pay for everything because the U.S. government is not moving us back home. If we were moving back home, everything would be paid for. But because we're moving from one location to another, it's all on us. Like, even if it was because the owners want to move us. The UK has something called no-fault eviction. So they could just tell you that they want you out for no reason. That is ending as of next month. So I suspect that may have also played a factor into it as far as the timing goes. Oh, don't I wish we were in a castle? No, we live in this very nice little... It's a town. It's really hard to compare from the US to the UK because, like, the things that are here are just so much older. And it's like, oh yeah, well, this is a little town, but it's got 10,000 people and a cathedral. So technically it's a city, or it's like, because it's been around since like the 1200s, it's got a cathedral, so it's a city. But it only has 200 people. There's also just so much less room to live or to put new housing in and all that stuff. Because the UK government has done a really good job of like limiting the amount of like land usage. So they do have to put in higher density stuff and replace some of the older buildings that are not like, historically preserved. Yeah, absolutely. I think the ones in town here were built in the 1800s, so it's not like it's super old. This town had, there were people here dating back to way back when, but it became big in Queen Victoria's reign. They found out that there's like a mineral spa in town, and so they were like, well, we're gonna, send everybody up here on holiday, and so they end up leaving wherever to come to North Yorkshire, and then they're like, oh look, a spa town. And I mean, Yorkshire in general is known for spa towns, like all over. There is Bath down south, of course, but like people wanted to escape all of the other people who were going to Bath, and so they were like, well, let's find a different. Queen Victoria was essentially like, let's find another different place on the way up to Scotland, where she also had her her other major castle, Balmoral. That's it. So they found this place in North Yorkshire. There's like Queen Victoria statue, the Queen Victoria shopping plaza, the Queen Victoria... because essentially she turned this like sleepy little village into the thriving city it is today by coming up here and deciding that this was going to be the place. All right, anyway, so here we've got... Here we want to split this into two separate integrals. One is going to be take the top function, subtract the bottom function. So 8x minus x cubed is going to get us the distance between this top layer and this bottom layer here. So we'll just outline this in the salmon color there. Plus, and then we take the integral here. Ugh. It's a little gross, but all right. Which then goes from 1 to 2. And here we've got 8 as the top function minus x cubed as the bottom function. Now, this is perfectly serviceable. It works just fine. It's easy to find the answer to this. However, there is a much easier way to do this. It only requires one thing, and that is turn this thing the other way. So instead, what we can do, actually, hang on. Take all that, just copy and paste it. bring this down here. I'm missing one little piece, but that's fine. Okay, get rid of that salmon-y stuff. Get rid of the green stuff. Oh, okay. It's fine. All right. Put in the line that goes through 0 and 8. And instead of going that way, go this way. And say, like, we're just going to find the distance that goes between the left and the right function. And this way, we only have two locations where this is going to, there's one scheme through which this works. We need to get rid of all this stuff over here. So here we say that, okay, we're going to take the integral of, this is going to be the functions, but in the y direction as our independent variable. So switch up which ones are which. In this case, again, this was y equals 8x. So make it x equals 1/8 y. And this was y equals x cubed. Great, make this x equals the cube root of y. So here, y to the 1/3 power minus 1/8 y dy is going to get us that integral in the y direction, using y as our independent variable. This goes from y values 0 to 8. Right? Lower value 0, upper value 8. That's it. No other fancy stuff going on there. So I highly recommend to all of my students, whenever you do this, look for the thing that's going to give you the fewest amount of calculations to run. Because here, right, if you make the same, if you have the same percentage chance of making just a simple copying error or something like that, the lower one has fewer things to copy. So you're going to have fewer chances to just make accidental mistakes that slip you up. Yeah, the site of the Roman baths is just named Bath. Yeah. I mean, yes, but at the same time, these particular functions are ridiculously simple to invert, so it's not really a problem. There are some considerations when you get more complex functions. But yeah, I get your meaning. You do have to watch out and make sure that you invert them correctly. And it is just more stuff that you're copying down. So it is perhaps, roughly speaking, the same percentage error of making some mess ups. Yeah. Yep. Right, so taking the integral of this one, we're going to get y to the 4/3, because we need to add 1 to the exponent, which is 3/3. So 3/3 plus 1/3 gets us 4/3. And then we divide by the new exponent, which is 4/3. So we multiply by the reciprocal, which is going to be 3/4. Minus, this is 1/8, which is just the constant, times the integral of y to the first power is going to be 1/2 y to the second. Right, and then, nope, we don't need a plus c because this is a definite integral going from 0 to 8. 0 is going to be fine for this, but it's also going to clear out all of our elements here, so they're gone. Okay, so we get a 3/4 8 to the 4/3. All right, this is going to be 16. So the cube root of 8 is 2, and then 2 to the 4th power is 16. Minus 1/16 times 8 squared is going to be 64. 64 over 16 is 4. Subtracted from 3/4 of 16 is going to be 12. So get rid of that. 12 minus 4 is 8. And I didn't actually copy down the answers, but that's fine. A, B, C, D, and E. How rude of me. Pen, what'd you do today? Right, and we got B, 8. And if somehow you have not followed Penn Center yet, please make sure to rectify that situation. Penn Center is a math streamer and also really loves Zelda, particularly Ocarina and Majora. I think Ocarina is the biggest one, but great. Then we'll copy down question 32, just so that we can hit that right after ad break. First 6 questions of the Canadian Euclid Math Contest. Nice. Which of the following expressions gives the area for the shaded region? All right, like I said, we're going to ad break real quick here. Go on, get up, stretch, grab your water, cycle it out, whatever you need to do, and we shall return shortly. Thank you so much, everybody, for coming. My name is Obi-Wan Pez. This is in Simplex Pachinko. Be right back. Righto. Oh, marking. Okay. Sorry, pen. I thought for a second that said making. I was like, but if you're making it on stream, isn't that going to be a problem? I got you. Oh yeah, I also didn't actually shade anything for anybody who was curious which region. It's pretty obvious which region it was going to be, but you know. Okay, but I also didn't list the actual equations. Okay. Okay. And may as well, right? That's going to be hard to do. A, B, C. That was a terrible idea. D, E. Okay. Integral from 0 to pi over 2 of 1/2 bracket parentheses root 3 sine theta end square minus open 3 cosine theta end square d theta. B, integral from 0 to pi over 6 of 1/2 3 cosine theta squared d theta plus pi over 6 to pi over 2. Hey Damie, how's it going? Good evening and welcome everybody. My name is Obi-Wan Pez. We do mathy type stuff here on Mondays and Wednesdays, and the rest of the week, whenever we feel like it, we do gamey type stuff. Recently, we've been playing Blueprints, Elite Dangerous, Baldur's Gate 3. Yep. We finished up a couple of other games somewhat recently. I could actually look at my list here. Every so often we play Astroneer. We'll also throw some Balatro in there whenever we just kind of get bored and need to fill time. And Rise of Piracy, which is an Irish John Games special. So, if anybody doesn't know Irish John, yeah, there we go. You can go check his stuff out. Rise of Piracy is kind of a fun little pirate type game. Get to captain your own ship, and then eventually your own fleet, and then eventually try to take over the world. So, as one would expect. All right, root 3 sine of theta parentheses squared d theta. C, whoa, hang on. Integral from 0 to pi over 6. 1/2 parentheses 3. Nope. Root 3. That's fine. Sine theta and squared d theta plus pi over 6 to pi over 2 times 1/2 3 cosine theta squared d theta. D 0 to pi over 3 1/2 parentheses 3 cosine theta squared d theta plus pi over 3 to pi over 2 1/2 root 3 sine theta squared d theta, or E integral from 0 to pi over 3 1/2 root 3 sine theta. Thank you so much for the follow. Hope you all are having a good night. Get that. Okay, there we go. That's squared d theta plus integral of pi over 3 to pi over 2 1/2 3 cosine theta parentheses squared d theta. Okay. So what's the correct way to go about doing this in the first place is we're going to look at, because this is in polar coordinates, we're looking at individual sectors. Which we can come up with from, like, looking at how do we get from area equals pi r squared for the whole circle to then a sector. Here we go, A equals, rather than pi r squared, the whole circle is going to be based on 2 pi. So if we remember, right, this is going to be like a 2 over 2. So 1/2 times our angle times r squared. Hey, PhD Lingo, how's it going? Yeah, took me longer to copy all the potential answers than it is to probably solve it. So what we're really looking at is here our area is going to be, again, 1/2 theta r squared, and r is going to be a function of theta in the first place. So when we start thinking about, like, okay, what are we going to do for calculus type stuff? What we're going to be doing is looking at infinitesimally small sectors for a particular function, which may have different radii based on our, like, current value, whatever it is we're doing. So here we're going to go with, like, this is our ds, which is the ds is going to be the arc length. Here we have our r of theta for each one of these things. And then here we have this d theta, which is going to correspond to our ds. The arc length, infinitesimal arc length. It's going to also be referred to by our d theta, the infinitesimal angle change. So effectively what we're doing here is we're going to say, okay, we want to sum as our n goes to infinity for I equals, here we go from 0 to n, right? And we want the sum of all of our sectors, or sector areas. So the areas are 1/2 times our delta theta. We can kick to the end because we like to have the, deltas are infinitesimals all the way at the end, just because. Right? And then here we say, okay, this is going to be r as a function of theta. Theta sub I, just to make it slightly easier notationally. Squared times delta theta. In theory, our delta theta could also be an I, because you could change the infinitesimal based on whatever you feel like. But, we don't do that. Generally speaking, we just say, look, just let delta theta be the same all the way through, and it won't be a problem. But, as n goes to infinity, it's not going to matter whether the delta thetas are bigger or smaller than each other. There's going to be an infinite number of them, so they're all going to get tinier and tinier and tinier. And eventually, this all ends up being equal to our integral, where we start from theta 1 going to theta 2, and it's going to be 1/2 r of theta squared d theta. All right. Anybody have any issues with that? I think that's pretty much what all of our options are here. So okay, so then the real question at this point becomes, which scheme are we using to calculate our integrals? So for this one, let's move over here. Let's take this, go like that, and then drag it over to the side. That's great. I love it. Love that for us. What we're going to do is look at it this way, and then we're also going to, that was brilliant. Let's also shift add, question mark. Yeah. Add all that. So let's go like this, and let's blow it up real big. Because we're going to look at this real close here. So looking at the other things that we have, right, you might look at the first formula and be like, oh, well, yeah, this is going to be like the first curve minus the second curve. And that works great if we were going kind of like this way and trying to get some sort of area like diagonal. But the problem is that that's not how polar coordinates work. Right? Polar coordinates always start from 0, from our origin point, and then work their way out. So I need to move that one here. Okay. they always start at the origin point and move their way out. So to calculate the area under the sine curve, what we're doing is we're going to start from 0, which at theta equals 0, we get 0. And as theta increases, our sine function is going to increase in value going up this way until we reach this point where the intersection is. Now, if we're doing an integral along this sine curve, it's taking areas of these like tiny sectors going like this. And again, these are supposed to be infinitesimal. So, yeah, okay, they're not quite infinitesimal, but, you know, it's fine. We could pretend. Right? Get enough of them, and it's an infinitesimal. So, we're getting the area under the curve here on this sector, or these sectors put together, until we get this sort of like lemon wedge sort of thing going on here. Right? And then we're going to say, okay, then we're going to switch to taking the integral of the cosine curve. Now, what does a cosine curve do? Well, it starts from 0, being cosine of 0 being 1. So that gets us a value of 3. Now we're way over here. So what's that going to mean? Well, at theta equals 0, it's way out here. We can't use this, right? We're not calculating these areas here. We're not doing that. What we want is not those areas, but the areas here, and here, and here, and here. All of these areas that are inside of this slice, right? This partial circle here. Well, the sum of all the sectors that get us this stuff, the area of this section. I guess that's a cap, right? Well, a cap's three-dimensional though. Okay, but anyway, so what we're looking for is, what is this point right there? We need to know what theta is equal to for each of these particular functions, because it doesn't have to be the same. Right? So if we call this one R1 and this one R2, we need what is theta R1, and then we also need theta R2. Right? They don't need to be the same. Oh, wait a minute. No, they are the same. Never mind. Jeez. Yeah, because this is the same literal angle. Never mind. Right, because we're measuring our angles in the standard way. We're starting from our origin point. We've got the initial side along the positive x-axis and the terminal side along the end, the friggin' A, along the ray that goes to wherever we are on those circles, yes, but our circles just stop short. So, you know, yeah, sure, this one here will hit here on that circle and here on that circle, but that's the same angle. Right. So positions are different, but the angles are literally the same. Okay. Sorry, I needed to just think about that for a sec. It's obvious when you say it like that, but still. All right, so theta R1 is equal to theta R2. So then we need to figure out where that particular location is, where we need to switch from one integral to the other integral. Okay, so we've eliminated a because obviously it's not the 1 squared subtract the other squared. Also, that is washer method. Yeah, that's the washer method. Or yes, yeah, that's the washer method. So we're looking at like what happens when you take cylinders. You have one cylinder with another cylinder inside of it, and you've like removed the one on the inside. So that has nothing to do with this particular problem. They're just trying to make sure that you understand that, yeah, that's not this one. That is not the correct setup. The rest of them have different combinations of pi over 3, pi over 6, 0, and pi over 2. So what we're interested in is when neither of these are going to be particularly nice in terms of like the actual sines and cosines of this particular angle is not going to just give... Hang on. Ow. Well, okay, the sine and cosine give you the same x and y values, but so just from drawing it, it looks like it's going to be pi over 3 as the angle in question. But of course, we can't just like assume that that's true based off of a drawing, because I draw terribly, and notoriously I have been known to draw things intentionally incorrectly. So be careful. Right, so what we want, let's see. Nope. That should be 1.5, which is also going to be essentially incorrect because of, yeah, it's going to be incorrect in terms of which one's higher and lower. Tibbies! Yeah, she's great. Love her content. So, yeah, actually, this right here, right? Now, I will say, like, the people who made the book, right, did at the very least put in, like, these equations into a calculator and graphed those equations. So it's not going to be what I just did here. You notice that this is 1.5, and like this is about 1.6. I don't remember what square root of 3 is. Oh, 1.73. Okay. So like that's significantly larger. So the other one, the smaller circle, should be larger than it is compared to where the larger circle is. But like, as long as you understand that, you shouldn't be using these in order to actually get the answer. These are just an illustration which may help you a little. Then, it's fine. Don't worry about it. Okay. So from here, we want to know when do we get the same coordinates? So there's a few ways to go about it. Let's think about it. How do we actually do this? Pretending that we don't know what the answers are, right? Oops. Okay, so we get like the small one here and the big one here. Sure, why not? How do we know what that is? So if we draw an angle down like this, this is theta, the theta in question. And so our R values should be the same as each other. Ugh, that's gross. Which does mean our tangent value is going to have a particular value to it. So here, root 3, yeah, nice. Okay. Root 3 sine theta needs to be equal to 3 cosine theta. And so this is going to be sine theta over cosine theta, which is tangent theta. It's going to be equal to 3 over root 3, which is just root 3, right? Yep. Or root 3 over 1 if you insist. So sine over cosine, again, not drawn to scale. It's going to be a root 3 opposite over adjacent 1. So theta is going to be equal to arctangent of root 3, which is equal to pi over 3. Yes. Woof. Having a day. Okay. So that pi over 3 is going to be where we want to break. So we're going to be taking the integral of the smaller circle, which is the root 3 sine of theta. Integral from 0 to pi over 3 of root 3 sine of theta. And then we said that this needs to be 1/2 r squared d theta. Then we're adding to that going from pi over 3 to, where do we get 0 again? Well, that side. Where do we get 0 again with a cosine function? That's at pi over 2. 1/2 times parentheses r squared, which in this case is 3 cosine theta squared d theta. Right, so then we just go with matching. Which one is it? Is it E? Yep. It's E. So the square part comes, I'm on the wrong mouse. The square part comes from the areas of sectors. So if you think about it in terms of the area of a circle, it's pi r squared, or a half of 2 pi r squared. 2 pi being the full angle to get you the circle. And then the 1/2 sticks out front. So then our sector area becomes 1/2 theta r squared. Our r's were a function of theta, and our theta as like a sliver is going to become d theta instead. So then we do our usual thing. I did this like every single day in my Calc 2 class, and my students got so pissed off at me. I was like, okay, we're going to start with the formula for one thing, and then we're going to do all of the infinitesimals, and then build the formula out of it to say, oh, look, this is the definition of integral. And they're like, we get it. I'm like, do you? Do you? Let's do it again. And they actually did appreciate it when it came to like polar coordinates, because they were like, oh my god, this is terrible. And I was like, okay, how do you find the area of a whole circle? Great. How do you find the area of a sector? Think about it in terms of how you find it from a whole circle, break it down into sectors. And then every infinitesimal sector you now build up into the whole curve, in like funny shaped curve. And they're like, oh, I'm like, there you go. It's easy to forget the easy stuff, yeah. All right, cool. Well, I think that's going to do it for tonight, and it's getting really quite warm in here, so I'm going to be happy to open that door, shut off the light, and just blow all the hot air into the hallway. That's the other thing about this room. I can't open the window because there's no such thing in Britain as like bug screens. And they definitely have moths. And I have wool stuff. Yeah. Like, they never need screens, really. I had, in our old place, I had that double French door open, like, basically 24/7. And it never was a problem. But for here, where this is going to be kind of interesting, they usually do have a little like flap at the top of the windows, which goes out to like a little strip along the top of the window, which allows airflow, but usually keeps bugs out. So maybe that'll work. We'll see. Let's go chat with Curly. She is currently working on Enshrouded, and looks like making a base. We are also technically unofficial friends of, anyway, the Knowledge Fellowship, or TKF. If anybody knows the Knowledge Fellowship people, TKF, we do a lot of stuff like adjacent to those people. They're quite wonderful. People like Dr. Danny Anduza, aka Paleontologizing. Zach, I believe, has an actual affiliate, like team affiliation with TKF. I might do it at some point. Thinking about it, it's kind of interesting. And at any rate, we'll be back probably tomorrow with more TTRPG prep work. I'm trying to get more ahead of my my party instead of being like, a day ahead. I'd like to be weeks ahead. We'll see how that goes. And then we'll be back on Friday for more gamey type stuff. And yeah, gonna have some fun. So anybody who's just here for academic type stuff, Mondays and Wednesdays. Mondays is going to be math communication, and Wednesdays are going to be calculation, like what we're doing here. So